Hello everybody. Today we start to discuss problems from American Physics Olympiad 2010 USAPHO Semifinals. This semifinal consists of 2 days. First day there were 4 problems, and second day there were 2 problems. For each day they gave competitors 90 minutes for all problems. So now problem A1. An object of mass m is sitting at the northmost edge of a stationary merry-go-round of radius r. The merry-go-round begins rotating clockwise with a constant angular acceleration alpha. The coefficient of static friction between the object and the merry-go-round is mu s. First question. A. Derive an expression for the magnitude of the object's velocity at the instant when it slides off the merry-go-round in terms of mu s, r, and alpha, and any necessary fundamental constants. Question B. For this problem, assume that mu static equal 0.5, alpha equal 0.2 radians per second square, and r equal 4 meters. At what angle, as measured clockwise from north, is the direction of the object's velocity at the instant when it slides off the merry-go-round? Report your answer to the nearest degree in the range from 0 to 360 degrees. US Physics Olympiad 2010 Semifinal. Problem A. The spherical shell of inner radius A and the outer radius B is made of a material of resistivity ρ and neglectable dielectric activity. A single point charge Q0 is located at the center of the shell. At time t equals 0, all of the material of the shell is electrically neutral, including both the inner and outer surfaces. What is the total charge on the outer surface of the shell as a function of time for t greater than 0? Ignore any effects due to magnetism or radiation. Do not assume that B minus A is small. US Physics Olympiad USAPHO Year 2010 Semifinals. Problem A 3. A cylindrical pipe contains a movable piston that traps 2 moles of air. Originally, the air is at 1 atmosphere of pressure P0, a volume V0, and at a temperature of T0 equal 298 Kelvin. First, process A. The air in the cylinder is compressed at constant temperature to a volume of 1/4 V0. Then, process B. The air is allowed to expand adiabatically to a volume of V equal 15 liters. After this, process C. This piston is withdrawn, allowing the gas to expand to the original volume V0 while maintaining a constant temperature. Finally, process D. While maintaining a fixed volume, the gas is allowed to return to the original temperature T0. Assume air is diatomic ideal gas. No air flows into or out of the pipe at any time, and that the temperature outside remains constant always. Possibly useful information. Cp equal 7/2 R, Cv equal 5/2 R, 1 atmosphere equal 1.01 10 power 5 Pascal, R equal 8.31 joules per mole by Kelvin. Questions. Question A. Draw a PV diagram of the whole process. B. How much work is done on the trapped air during process A? C. What is the temperature of the air at the end of the process B? D. What is the lowest pressure occurs during total cycle? US Physics Olympiad 2010 year, USAPHO Semifinal. Problem A4. The energy radiated by the sun is generated primarily by the fusion of hydrogen into helium-4. In stars the size of the sun, the primary mechanism by which fusion takes place is the proton-proton chain. The chain begins with the following reactions. First reaction, 2 protons go into element X1, positron E+, and element X2. The second reaction is proton plus element X1 going to element X3 plus gamma ray. The amounts listed in parentheses are the total kinetic energy carried by products including gamma rays. P is a proton, E plus is a positron, gamma is a gamma ray, and the X1, X2, and the X3 are particles for you to identify. The density of electrons in the sun's core is sufficient that the positron is annihilated almost immediately, releasing the energy X. During this annihilation reaction, electron plus positron go into 2 gamma rays. Subsequently, 2 major processes occur simultaneously. The PP1 branch is the single reaction. 2 elements X3 go into helium-4 plus 2 elements X4, which releases an energy Y. The PP2 branch consists of 3 reactions. First reaction is element X3 plus helium-4 go into element X plus gamma ray. Next reaction, element X5 plus electron go into element X6 plus element X7. And last reaction is element 6 plus element 4 go into 2 helium-4 particles, where Z is the energy released in step 6. So, questions. Question A. Identify X1 through X7. X2 and X7 are neutral particles of negligible mass. It is useful to know that the first few elements in order of atomic numbers are hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Question B. The mass of the electron is 0.51 megaelectron-volt per c square. The mass of the proton is 938.27 megaelectron-volt per c square, and the mass of the helium-4 nucleus is 3727.38 megaelectron-volt per c square. Find the energy released during the production of one helium-4 nucleus including the kinetic energy of all products and all energy carried by gamma rays. Question C. Find the unknown energy X and Y above. Question D. Step 6 does not proceed as follows because there is insufficient energy X5 to X6 plus positron plus X7. What constraint does this fact place on Z? And question E. In which of the reaction steps is the energy carried by any given product the same every time the step occurs? Assume that the kinetic energy carried in by the reactants in each step is negligible, and that the products are in the ground state. US Physics Olympiad, year 2010, USAPHO, Semifinal. Problem B1. A thin plank of mass big M and length big L rotates about a pivot at its center. A block of mass M small, much less than M big, slides on the top of the plank. The system moves without friction. Initially, the plank makes an angle θ0 with the horizontal. The block is at the upper end of the plank, and the system is at rest. Throughout the problem, you may assume that θ much less than 1, and that the physical dimensions of the block are much smaller than the length of the plank. Let x be the displacement of the block along the plank, as measured from the pivot, and let θ be the angle between the plank and the horizontal. You may assume that the centripetal acceleration of the block is negligible compared with the linear acceleration of the block up and down the plank. Questions. Question A. For a certain value of θ0, x equal k θ throughout the motion, where k is a constant. What is the value of θ0? Express your answer in terms of big M, small m, and any fundamental constants that you require. Question B. Given that θ0 takes this special value, what is the period of the oscillation of the system? Express your answer in terms of big M, small m, and any fundamental constants that you require. Question C. Determine the maximum value of the ratio between the centripetal acceleration of the block and the linear acceleration of the block along the plank, writing your answer in terms of small m and big M, therefore justifying your approximation. Question D. Count what is kinetic and potential energy of the system in any particular moment. US Physics Olympiad, year 2010, USAPHO, Semifinal. Problem B2. These three parts can be answered independently. Part A. One pair of ends of two long parallel wires are connected by a resistor. Resistance equal 0.25 ohms, and a fuse that will break instantaneously if I0 current through it equal 5 ampere of current passed through it. The other pair of ends are unconnected. A conducting rod of mass M small is free to slide along the wires under the influence of gravity. The wires are separated by L equal 30 centimeters, and the rod starts out distance A equal 10 centimeters from the resistor and the fuse. The whole system is placed in a uniform constant magnetic field of B equal 1.2 Tesla, as shown in the figure. The resistance of rod and the wires is neglectable. When the rod is released, it falls under the influence of gravity, but never loses contact with the long parallel wires. Questions. 1. What is the smallest mass needed to break the fuse? 2. How fast is the mass moving when the fuse breaks? Part B. A fuse is composed of a cylindrical wire with the length L and radius R much smaller than L. The resistivity, not resistance, of the fuse is small and given by a raw fuse. Assume that a uniform current I flows through the fuse. Write the answer below in terms of L, R, rho F, I, and any fundamental constants. First question. What is the magnitude and direction of the electric field on the surface of the fuse wire? Second question. What is the magnitude of and direction of the magnetic field on the surface of the fuse wire? Third question. The Poynting vector S is a measure of the rate of electromagnetic energy flow through a unit surface area. The vector gives the direction of the energy flow. Since S equal 1 over mu 0 multiplied by cross product electric field by magnetic field, where mu 0 is the permittibility of free space and the E and B are electric and magnetic field vectors, find the magnitude and the direction of the Poynting vector associated with the current in the fuse wire. Part C. A fuse will break when it reaches its melting point. We know from modern physics that a hot object will radiate energy approximately according to the blackbody law at power equal sigma A T power 4, where T is the temperature in Kelvin, A is a surface area, and sigma is a Stefan-Boltzmann constant. If T fuse equal 500 kelvins is the melting point of the metal for the fuse wire, with the resistivity rho equal 120 nano-ohm by a meter, and I fuse equal 5 ampere is the desired breaking current, what should be the radius of the wire R?